Okay, so we just saw some very basic examples of dimensional arithmetic, as I like to think of it, right? The idea that since physical quantities carry dimensions along with them, that means that when we write them down in different equations, we know that the dimensions all have to agree with each other because of exactly what I've written here. Things where you're adding together or comparing things that have different dimensions are basically undefined gibberish, right? And I promised that using this kind of thinking together with the kind of estimation style of estimating numbers that we talked about earlier in the chapter can help us, understand things in the world, even if we don't have the technical expertise to know exactly what's going on. So this is going to be the first of 2 case studies to kind of give you a flavor of what I mean when I say that. Right? So let me pull up this picture. This is a series of photographs of the Trinity nuclear test. Right? So this is a very sad photograph on July 16th, 1945. Humanity detonated the first atomic weapon out in the deserts of New Mexico. And of course, all of the details of this nuclear test were completely secret, right? And, people knew very little about what was going on. And for instance, for a long time, even how powerful these nuclear weapons were was a closely held secret, right? On the other hand, these photographs appeared. These photographs were published even before all of the details of the test were declassified. And actually, just by thinking about the dimensions involved in this kind of a problem, you can figure out, you can get an order of magnitude estimate of how powerful these atomic bombs were without knowing anything about atomic fission, shock waves, explosions, anything like that. Just using our physical intuition and thinking about the dimensions of the problem involved. So how is that even possible? Let's explore that question. So I'll get rid of this for now, and let's dive right in. Right, we want to think very systematically about the information that is contained in that photograph. And so maybe I put it away too quickly. Let me kind of show you what's being displayed here. This is a sequence of photographs in time. So in this government photo, right in the bottom left of each of them, there's a label of how long since the explosion happened this photograph was taken, right? So it's 0.006 seconds all the way through, in this case, about 0.1 seconds. There's actually a whole series of these photographs that cover even more time points. And then what we're seeing is this explosion, is this blast wave, right? Or this shock wave propagating outward. And so what we can see just from these photographs is like a explosion, a blast radius that gets bigger over time. And that's the information that we're going to start with to figure out, well, how powerful was the explosion that caused this blast? Okay, how do we do this? So what we want to say is, how much energy caused that blast? And the data we have is like size of the explosion versus time, right? Because we could go into those photographs. I don't know if you noticed, but in addition to the timestamp, there's also this scale bar. So we could use this scale bar to say, okay, at any particular time point in this photograph sequence, I know how big the explosion was. So that's the data we're going to work with, okay? How do we even get started? What we're gonna do is say the data we have is in the following form. The radius of the explosion, I'm going to use the symbol r to denote the radius, and we could measure it as some function of time, right? The key here, of course, is that we have no idea what this function is. Computing this function requires knowing all of the details. How does, a shock wave propagate through the atmosphere? How do things explode? What is going on? We're not going to try to compute this function. What we're going to do, though, is say, dimensional analysis tells us that the units of these two sides of the equation have to agree. So whatever the dimensions of the radius of the explosion is, have to be the same as the dimensions of this function of time. Okay. And again, just to emphasize, when I say radius of the explosion, I'm basically pretending, order of magnitude estimating, that this explosion is close to a sphere. As you can see, especially at later and later times, it's definitely not a sphere, but as a rough order of magnitude estimate, we're going to pretend it's a sphere which has a particular radius defining it. Okay. Now, so far, this is not very helpful, right? I mean, I guess we know that both radius and because it appears in this expression, whatever this function is, have to have dimensions of length. That's how we're choosing to define the size of the blast in terms of just a length. But we don't know very much else. So here we start putting more and more of physically what we know about the situation into this problem, into this expression, right? So how do we do this? So, we say what really is, this function of time, right? This way that the blast gets bigger as time elapses. And the key here is that we know that this is not actually only a function of time, right? F of t has to also depend on lots of other quantities, right? For instance, surely the function that determines how big the blast is over time depends not only on time, but say also on the energy that caused the explosion in the first place, right? If you have like a tiny firework, the rate at which that explosion grows initially is presumably going to be very different than the way an atomic explosion progresses, because the energy scales are so different. So presumably the explosion depends not only on time, but also on the energy, which I'll label with this capital E. Right? You might also say that how the explosion propagates through the air should depend on the air, right? So I'm going to say it depends also on the density of the surrounding medium, right? And that also, I think, makes physical sense. If you imagine carrying out an explosion underwater, for instance, you might imagine that the size of the explosion is very different because it's expanding against, water, which is much harder to move aside than air is, right? So when I've written down, R is a function of time, really it's a function of lots of stuff. It's a function of time, energy, the density of the atmosphere, so on and so forth. And this is where, we put, that's a terrible arrow, this is where we put our physical intuition. Physical intuition / knowledge of the world, right? It goes into, what we know this function actually has to depend on, right? That's great. So now we can finally start thinking more seriously about dimension analysis, because even though we still have absolutely no idea what this function is, because none of us are experts in nuclear explosions, we still have the constraint that the dimensions of R, length, have to match the dimensions of whatever this function is, f of t, energy, and density. Okay, so again, all of this has to have dimensions of length. Now we can start kind of systematically working through some of the algebra to help us out. Okay, here's what we're going to do. So what we want f of t, energy, and density, this has to equal length. We know things like the following. Each of these components, the things that the function depends on, we know what all of those units are, right? So for instance, we know that the dimensions of time, well, that's just time. We know that the dimensions of energy, well, that's just mass times a length squared, divided by 2 powers of time. Let me just write that more clearly, time to the -2. And we know that in this case, the units of density, we're talking about air in 3 dimensions. So this is going to be a mass divided by 3 powers of a length. So mass, length to the -3. Okay. So we have to come up with a combination of these components of the function, and I apologize for not putting the brackets here around density. We have to come up with a combination of all of these components that, when we multiply them together, conspire to give us just dimensions of length, okay? And we know we can't add these things together because adding things that have different units or different dimensions doesn't make sense, right? So what we have to do, that means we want a combination such that, dimensions of length is given by some way of multiplying times and energies and densities together, right? So I'll write that by saying length is equal to whatever the dimensions of t are to some power, so I'll call that to the power of x, multiplied by the dimensions of whatever energy is to some other power, energy to the power of y, multiplied by, these dimensions of density to yet another power. We're trying to find a particular way, again, of multiplying these times, energies, and densities together so that when we mush everything together, the dimensions of the composite object is just length, because dimensional analysis tells us that's what it has to be, right? Another way of saying this, is that this function f of t, e, and rho has to be some quantity which maybe I'll call A, multiplied by f star of t and rho, where the idea is that this quantity A has all of the dimensions in it. So A is equal to, dimensions of A is equal to length, and this f star thing is just a number. So it has, I'll just call dimensions of 1. So maybe we break the function up into something that has all of the dimensions in it, multiplied by something which is just a complicated number that, in principle, is very hard to compute. Okay? So we're trying to find this dimensional combination of all of the things that we know the function depends on that gives us the right overall dimensions. Okay. So now what we can do is, substitute all of these pieces into our algebraic expression. We know what the dimensions of time, energy, and density are, and so we can see what that gives us. That tells us that the dimensions of length, the size of the blast, right, has to be, well, if I pull together, say, all the factors that depend on time, I know that it's going to be time to the power of x, and I know that time also appears in this energy expression with a -2, right? So that's going to be t to the x minus 2y. What things depend on, say, the next dimensional quantity in any of these things? That could be mass. So mass, it depends, energy depends on mass, so that's going to give me a power of y. And density depends on mass, so that's going to give me a power of z. So I have mass to the y plus z. And finally, I have dimensions of length. The things that depend on length are, again, the energies to the y and the densities to the z. So I see that energy to the y, that's going to give me L to the 2y minus 3z coming from the density, right? Now, if you like, so this all has to equal just length. And if you like, you can think of it as this all has to equal length to the 1 times time to the 0 times mass to the 0, because things to the power of 0 are just unity again, right? So this expression is actually a system of basic algebraic equations, right? It tells me that, whatever power of length is here has to match the powers of length over here. So, for instance, it tells me that 2 times y minus 3 times z has to be the number 1 in order for these two sides of the equation to match each other, right? Similarly, if I look at this mass term, it tells me that y plus z has to be 0 because mass doesn't appear on this side of the equation. And if I do the same thing for this time combination, it tells me that x minus 2y also has to be equal to 0, right? So I have 3 equations in 3 unknowns, and that means that I can solve to figure out what each of these x, y, and z are, right? So, how do you imagine doing that? For instance, this equation tells me that y is equal to minus z. And then if I plug that answer into this expression, so if I feed that into here together with this, that tells me that 2y plus 3y is equal to 1. So for instance, that tells me that y is equal to 1/5, and z is just minus y, so z is equal to minus 1/5. And then I plug those answers into my last expression, and I realize that x has to be 2/5. Okay, so by thinking about forcing the dimensions of the two sides of the equation to agree with each other, we've learned that this has to be the particular combination of how time and energy and density all get multiplied together, right? So that means, so if I just write that out more explicitly, so x is 2/5, y is 1/5, and z is minus 1/5. That means that I can write my equation. Remember, I had r was equal to some function of f of t, energy, and density. That means that I actually know that r has to be, first, to get the units right, something that looks like density to the minus 1/5, because z, the minus 1/5, was the thing sitting in front of the density. So this function has to be density to the minus 1/5 multiplied by energy to the positive 1/5 multiplied by time to the 2/5 times something, right? Times something that doesn't have any dimensions associated with it at all, right? And up above, I think I called that f star. Here, I'm just going to call it c, some constant. Okay, where, c is a constant that depends on detailed physics. detailed physics. And, you know, a priori, you don't necessarily know what C is exactly equal to without doing a detailed calculation. But in fact, very typically in these style of dimensional analysis problems, if you remove all of the dimensional dependence, the thing that's sitting out front is typically a number that's about 1. You know, it might be a tenth, it might be 10, but it's typically pretty close to 1. In this case, actually, if you do the calculation, it turns out that it's very close to 1. So it's just some number. Right. Now, if we rearrange this expression, you know, we have the radius as a function of time, energy, and density, and it has to be a function that depends in this kind of combined way, just for dimensional reasons. I can rearrange this to solve for the energy, right? Because the question that we started with was how much energy was released to cause this explosion in the first place, right? So if I rearrange this expression, you know, what I'm left with is an energy, which is 1 divided by whatever this constant is, times the radius to the power of 5, times a density divided by time squared, okay? And actually, finally, we're in position, now that we've just done this dimensional analysis estimate of how does the energy have to depend on the size, the density of air, and the time that's elapsed, we can just go back to our photograph and, you know, pull up numbers for these different things. So for instance, if I look at this first photograph, you know, I'm going to use a value of time equal to this value of time. I'm going to use these scale bars, and I'm going to kind of measure this distance here, right, and compare this to my scale bars. It's about 3/4 of this, so it's about like 77 meters or something like that. And then I'm just going to plug that into this expression, right? So for instance, I have energy. You know, this is an order of magnitude guess, but it's something that's close to 1 over 1, that's about 1, times a radius of about 77 meters to the power of 5. The density of air, that's about 1.2 kilograms per meter cubed. And how much time elapsed, we said in the photograph we happened to be looking at, that was like 1 over 0.006 seconds squared, right? And if I combine all of those numbers together, I get 9.0 times about 10 to the 13 joules, right? And okay, the yield of bombs is typically not reported in joules, it's reported in how much TNT would create an equivalent explosion. You know, it turns out that 1 kiloton of TNT, I always have to look this up because I don't care that much, is about 4.184 times 10 to the 12 joules. Okay, so doing this unit conversion, that means the energy that caused that blast, we estimate just by thinking about units and looking at a photograph. We estimate this, if I just multiply all these together, that's about 21.6 kilotons of TNT. And again, in some ways, this is kind of an order of magnitude estimate, especially if we don't know that this number is really actually close to 1. You know, it could be a half, it could be 2, it could be something in that ballpark. So it turns out that it's very close to 1, so, you know, that's nice. But, you know, without knowing that, you just say this is about the order of magnitude that I think this explosion was actually generated by. And then just like in the Fermi estimation thing, you can say, well, we've made this estimate just by thinking about units. We said the way that a blast progresses in time has to be a function of the time that's elapsed, the energy that caused the explosion, and the density of air. And knowing that those were what it depended on was where we put our physics knowledge or our understanding of the world into this problem. Once we say that, we know what dimensional combination of those three things, time, energy, and density, have to be present in the problem just in order for the units to agree. And that gives us an estimate of the energy scale. And then just like in our other estimation problems, we go back and we say, well, how does that compare to either what we know about the world or, you know, anything else? In this case, you can go up and look at the most recent analysis. You know, what's the official answer to this question? The official answer is that the energy released in that Trinity Test explosion was 22 point something, 22.1 plus or minus 2.7 kilotons of TNT. That's, I mean, that is a remarkably accurate estimate, right? Like this estimate, again, just by looking at a declassified photograph, comes perfectly within the error bars of the official, formally classified estimate of what the value actually was, right? So, you know, not too bad for using only units and dimensions and not knowing literally anything about explosions, fireballs, shockwaves, fission, anything. How big the bomb was that created it, you know, how many atoms of uranium were used. You don't need to know any of that stuff. Just from a photograph and from dimensions, you get the right answer in this case. And in any case, kind of a good estimate of the right answer. Actually, this kind of back-of-the-envelope estimation for exactly this type of problem has also been used to estimate everything from like how powerful are supernova explosions of exploding stars to, you know, for instance, the tragic explosion that happened in Beirut just a few weeks ago. Just a few weeks ago, where, you know, before we knew what even caused the explosion, people were able to work out from, you know, Twitter videos of the shockwave what the relative energy scale was, and that helped us narrow down the set of possibilities of what could have caused the explosion in the first place. Right. Great. So that is case study 1.